a little bit more about how X works in the ice tables. For the reaction of molecular iodine gas, that's I2, into atomic iodine gas, that's I. The equilibrium constant Kc is 2.78 blah 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 times 10 to the minus fifth at 521 degrees Celsius. If the initial concentration of I2 is 0.15 molarity, what is the equilibrium concentration of I? Like I said, we're going to do a variety of ice table problems. Most of them, you know what Kc is. I'm going to just put in 2.78 times 10 to the minus fifth here. And what I think happens for this one, if you do the homework, is there are a variety of Kc's and a variety of temperatures. This is going to be an ice table problem in terms of molarity. And now we have 2I as our product. Let's zoom in a little bit here. For this one, we know that we start with 0.15 molarity, and we don't have any product. No mention of it. We do a minus x because the coefficient is 1, and then we do here a plus 2x. And that's because this 2 is the same as that 2, meaning, and all this plus 2x means is that x is the extent of reaction, or how much reaction occurs. And what we say here is, for every X amount of the iodine that reacts away, we do create twice as much of our product. That's what this reaction says. So, our equilibrium concentrations are now right here. Our equilibrium constant expression. And here's what gets tricky, and this is why I always write out the equilibrium constant expression before solving it. My equilibrium constant expression has a 2 here as well. That is also related to the 2 coefficient. I guess I can circle them all, right? All the places that 2's show up for the same reason. So now just over concentration of our reactant. Now I plug it in, whatever the equilibrium value is, so it's going to be 2x, and that is actually squared. 2x squared over 0.15 minus x, and it all equals 2.78 times 10 to the minus fifth. Any questions so far? Okay. Well, now, I don't know about you. Maybe you love solving the quadratic equation. I like to avoid the quadratic equation whenever I can, and as you can see, I made a mistake on the last one. So now on this problem, let's talk about whether or not we can avoid the quadratic. We can, because when Kc is less than 1.0 times 10 to the minus fourth, we may assume that x is small. Let's say this, when Kc is less than 1.0 times 10 to the minus fourth, we can assume that x, how much reaction occurs, is much less than 0.15, meaning that 0.15 minus x equals 0.15. And functionally what that means is that we're going to ignore x. And when I ignore this x term, my quadratic equation goes away. My simplification is now 2x squared over 0.15 equals 2.78 times 10 to the minus 5th. Now I bring my 0.15 up to the right-hand side. I divide through by my 2, and I get that x squared equals 2.78 exponent 5 minus times 0.15 divided by this 2, so 2.09 times 10 to the minus 6th. That's x squared. And x is the square root of that. And since I wrote 2.09 here, I'll actually do that. Exponent 6 minus. Then square root it, and I get 1.45 times 10 to the minus 3rd as my molarity. So let me zoom back out a little bit. Whenever you assume that you can ignore x because Kc is small, you have to check and see, is x less than 5% of 0.15, the number that it was ignored because of?
Professor?
Yes.
I thought we were to square the 2x.
Oh, thank you. Boy, thank you, Daryl. Let me go back and fix that now. So this should be a 4, shouldn't it?
It should.
Thank you. Let me go back. Otherwise, so I'm going to make a mess of this. All right, so 2.78 exponent 5 minus times 0.15 divided by 4 is 1.04 times 10 to the minus 6. Square root that, 1.02 times 10 to the minus 3rd. Thank you. So now, is it less than 5%? We'll take the number, divide it by 0.15, and multiply it times 100. And it's actually 0.68%. So yes. And that's just a good rule of thumb. What you can do if you really love numbers, and I have done this before, is you can solve it by making the ignore x approximation and then solve it by solving the quadratic, and you will find that the numbers you get are very close to each other. And therefore close enough for us to make this approximation.
Professor?
Yes, Aziz?
Yeah, how do you check the 5%?
So you want to take this number, yep. You want to take your x and compare it to, like, see how you ignored x to compare to the 0.15? You want to take as x 5% of the 0.15. And what that means is divide, so 5% of it would be take the number, divide it by the bigger, and times it by 100. Like that, Aziz.
Okay, thank you.
Sure. Now, let's get back to the actual question. What is the equilibrium concentration of I gas? It is actually 2x. So it's going to be 2 times 1.02 times 10 to the third. 10 to the minus third, I guess. And I get 2.04 times 10 to the minus third molarity. And thank you for your help with that. Any questions? Any other questions about this?